Let's talk about something that is called limiting reactant in the stoichiometry, or limiting reactant of the chemical reaction. So the idea is simple here. When you have two reactants reacting together, you want to know which one is limiting your reactant, meaning that which one is going to determine the amount of the product that you get. For example, if you have 4 chairs here and 5 people, then the number of the chairs is limiting, because at the end I will only have 4 people sitting on the chair. I can't have 5 people sitting on the chair, and we're talking about one person sitting on one chair. So in a simple case scenario, the one that is less is going to limit the process, and that's going to be the limiting reactant. But this is the simple case scenario when the ratio of the reactants, or the two things that interact together, is 1:1, meaning that one person needs one chair, right? In a different example, maybe a person will need two something else, two, I don't know, fruits or something. Now that becomes a bit more complicated, but we'll talk about it in the next slides. All right, so limiting reactant, right? So the one that is determining the amount of the product that is formed, because that is the one that gives less product. And so there's also something about the yield here. We'll discuss that in a little bit as well. First of all, whenever you need to find the limiting reactant of any reaction, you need to make sure that your chemical equation is balanced. And that is like for any other operation, any other thing that you need to do, any other calculation that you need to do with your chemical equation, you need to make sure it is balanced. Right, so let's say now this is a balanced equation. Let's start with something simple. Suppose I have 10 moles of H2 and I have 10 moles of O2. So I need to determine the limiting reactant. Now, here's the proper way how you do that. You do two separate calculations. One, you put 10 here, and you determine how much product you get based on this. So the ratio is 2:2, and so it's 1:1. And that means 10 moles of the H2 would produce 10 moles of H2O. All right, now you forget about this for a moment, you leave that aside. Then you do another calculation based on the oxygen. So I'm going to put 10 here. And based on the 10 moles, I just put it a bit higher so I can put two numbers here. 10 moles of the oxygen are going to produce, the ratio now is 1:2. So this time I'm going to have 20 moles of product. So which one is the limiting reactant here? Remember, the limiting reactant is the one that gives you less product, is the one that limits the process. So in this case, because the H2 gives you less H2O than the given amount of the O2, then in this case, this is going to be the limiting reactant. Okay, now let's change the numbers a little bit. Now let's say we have a different example. So let's say we have four moles of H2 and we have 6 moles of O2, right? And we need to find the limiting reactant. What do? Just like we did before. So do first for the hydrogen. You will put that 4 moles of the hydrogen will produce 4 moles of H2O, because again the ratio is 1:1. Then separate from this, you do the same for the oxygen. You write down that 3 moles of the oxygen are going to produce 2 times 3 divided by 1. The ratio is 1:2, so 2 times more. So I'll have 6 moles of H2O. And now which one gives you less? Right? So the hydrogen gives you less. And so in this case, again, this is the limiting reactant. One very important thing that you need to pay attention here. Even though we had the less oxygen, right? So this is less. I have 3 moles of the oxygen, I have 4 moles of the H2. But my limiting reactant is the hydrogen, because I need to consider the ratio of the reactants. It's not simply 1 to 1. Therefore, you should never determine the limiting reactant based on just looking at the amounts of the reactants. Just because the oxygen is 3 and the hydrogen is 4 doesn't mean that oxygen is going to be the limiting reactant. The limiting reactant is the one that gives you less product. And in this case, hydrogen gives me less product. So please remember that. Now, with this said, you can also do this a bit faster to find the limiting reactant generally, because the coefficients are important here. What you do is you simply get the ratio of the moles that you have with the coefficient, and that's going to be the efficient moles of the H2. You can look at it that way. So I can say that the N of the H2, the efficient moles of the H2, is going to be 4 divided by 2, and that's 2. On the other hand, the efficient moles. Okay, so again, limiting reactant is the one that determines the amount of the product. Now let's do this problem together. So let's say you have the ammonia reacting with the copper oxide, you're producing these products, and it is asking you if a sample contains 18 grams of NH3 and reacted with 90 grams of copper oxide, which is the limiting reactant, first of all, and how many grams of N2 will be formed. Let's first of all write down what we have. We have the mass of the NH3, and that's 18.1 gram. We have the mass of the copper, and that's 90.4 gram. And we need to find the limiting reactant, and we need to find the mass of the N2. Now, let's emphasize this one more time. Even if the problem did not ask to find a limiting reactant, you are still required to determine the limiting reactant, because the amount of the nitrogen that is formed is based on the limiting reactant. You can only determine how much product you had based on the limiting reactant, because maybe you'll have 18 grams of the ammonia and 1,000,000 grams of copper oxide. Just because you have 1,000,000 grams of copper oxide, it doesn't mean that all of it is going to react and produce your product. It's the limiting reactant that will tell you how much of that is actually going to react and how much product you will get. So the first step here is you need to find the moles. Let's do that. The moles of the NH3 are going to be 18.1 gram divided by 17 grams per mole. So 18.1 divided by 17, I got 1.06 moles. Second, I find the moles of the copper oxide, so it's going to be 90.4 divided by 63.5 plus 16. Yeah, it's one oxide, right? So I have 79.5, and now I have 1.14 moles of the copper oxide. Now do two calculations. Do one with the ammonia, so I'm going to put here 1.06 moles, and I'll find how many moles of nitrogen that's going to produce me. So nitrogen here is going to be, it's 2 times less, so it's going to be half of this. Zero 0.53 moles. And for the copper now, I do separate calculations for the copper. .14. The ratio is 3 to 1, so it's going to be the third of that number, 1. So this is going to produce 0.38 moles. Therefore, out of these two, because this produces less product, this is my limiting reactant, and it is actually how much product is going to be formed, 0.38 moles of nitrogen. And now to find the mass of the N2, I'm going to do 0.38 times 28. And that gives me 10.64 grams of N2. That's how much nitrogen I'll get. So once again, pay attention that we did all our calculations based on the limiting reactant. And that's the one that gives us less product. So on the slides, you will also have the method of using the dimensional analysis, right? So this is just showing you the molar masses. One step, you get the moles of the ammonia divided by 17. You do the mole ratio. Every 1 mole reacts with 2. Every 1 mole is produced from 2 because the ratio is 2 to 1. And that's the mole ratio, and that's how we find the number of the moles. Then you do the same thing with the copper oxide. Now let's also talk about the percent yield of the reaction. So the percent yield is the efficiency of the reaction. It is essentially, it's how much you expect it to have and how much you actually get. That's the ratio, how much you got and how much you expect it to have. So that's just like the efficiency of the reaction. Let's do some examples and you'll see how that works. So it says if 25 kilograms of nitrogen is mixed with 5 kilograms of hydrogen, how much of ammonia will be formed? Fine, we can do it. So we find the moles. It's going to be 25,000 because I have converted the kilograms to grams, divided by 17 grams per mole. The molar mass is in grams, that's why I need to do that. So I have 25,000 divided by 17, and that's 1,470 moles. And if I find the moles of the H2, that's going to be 5,000 now divided by 2, and that's 2,500 moles. All right, so 2,500 moles of the hydrogen will produce, I'm going to multiply again this by 2 and divide by 3, so 2,500 times 2, 5,000 divided by 3. That's about that number, 1,666. And now I do the same thing for the nitrogen. Right, so for the nitrogen, I'm gonna have 1470. The ratio is 1 to 2, so the nitrogen is going to be, the ammonia is going to be 2 times more, times 2. So I have 2,940 moles of ammonia being produced from this amount of the N2. Therefore, the limiting reactant is the hydrogen. It's 3,500 moles. Hydrogen is the limiting reactant. Now let's continue. So this number that we got, which is here, is the theoretical yield, right? As just the name states, theoretical yield means in theory. I haven't done this reaction in the lab. I've just calculations theoretically. I've done calculations theoretically on the paper, And I've seen that, okay, I need to have to determine the percent yield, I would take the actual yield and divide by the theoretical yield and multiply by 100%, and that will tell me the percent yield of the reaction, right? So we can also put it this way. The percent yield, remember, is equal to actual divided by theoretical times 100%. Now, I want to just go back for a second to the previous reaction. So let's say, so that was H2 plus N2, and it was giving us NH3. And we have seen that in theory, right? The theoretical yield of this reaction, the theoretical yield was 1650 moles. Now, if somebody tells you, okay, this reaction was run and 1200 moles have been obtained. So the actual yield, you would say that is 1200 moles. And by the way, the units can be anything. It can be moles, kilograms, grams. As long as they are the same, then you can divide them. So if somebody says that this reaction has been carried out and 1200 moles have been obtained, then the percent yield of this reaction would have been 1200 over 1650 times 100%. So that'll be about 73%. Right, so we calculate that we should get 1650, but we only get 1200. So the efficiency is only 70%, 73%. Something happens, maybe some of the reactant is lost, you get a side product, there was some kind of spill or anything, and that's normal. Any reaction has. So this is a summary of what you're supposed to do. You always need to find number of the moles, regardless. You need to also find the limiting reactant in order to find how much product you're getting. And that you're calculating based on the limiting reactant is going to be your theoretical yield. And the percent yield is going to be the ratio of the actual and the theoretical yields. Let's look here. It says methanol is used in race cars, right? And then it says a student reacts that much of CO with 8.6 grams of H2. Calculate the theoretical yield. So first of all, let's write down what we have. We have the mass of the CO, which is 68.5 grams. We have the mass of the H2, which is 8.60 grams. And we need to find the theoretical yield. So first of all, you need to find the number of the moles. Number of the moles of the CO will be 68.5 grams divided by 28 grams per mole. So let's calculate this. 68.5 divided by 28. So I've got 2.45 moles. On the other hand, if I find the number of the moles of the H2, I'm getting 8.60 divided by 2, so that's going to be 4.30 moles. Now let's do my calculation. So I put for the H2, I'll do two individual calculations, 4.3, and that's gonna produce me half of that, so it's gonna be 2.15 moles of methanol. And now let me do the calculation based on the CO. So I have 2.45 moles of CO, and the ratio is 1:1. So here I'm gonna get 2.45 moles. Therefore, because the hydrogen produces less product, it is actually the limiting reactant, right? So hydrogen would have given me 2.15, while these can give me more. That's why this is the limiting reactant. We're limited to how much hydrogen we have here. And that right here is the theoretical yield. Now, because it is asking us to find a percent yield and it is telling us how many grams of methanol is in fact forming this reaction, I'm also going to convert the theoretical yield into the grams, right? So this will be 2.15 grams times the molar mass of the methanol, which is going to be 31 or 32, 1 second. So I have 32. So 32 times 2.15, 68.8 grams. Again, this is what is expected to form in this reaction. That's the theoretical yield. It is telling me now, it is saying that actually 35.7 was formed. So the actual yield is 35.7 grams. Okay, therefore, to find the percent yield of this reaction, I'm going to divide these two. Percent yield is equal actual divided by theoretical. So I'm going to have 35.7 divided by 68.8. Times 100. So that's about, it's about 52%. I'll round off a little bit. So that's about 52%. Which again is reasonable. So you expect to have 68.8, but you got 35. That's about the half, a bit more than half. So it's about a 50% yield. Right, again, so doing bidimensional analysis, you'd have to convert the mass to moles, do the mole ratio here, then convert to the mass, and that's going to be your theoretical yield. And do the same here, you compare the one that gives you less, it is the limiting reaction. Let's do one more. Okay, it says when 2.84 kilograms of titanium chloride are reacting with 1 kilogram of magnesium, that's how much titanium is actually obtained. So that is your actual yield. Calculate the percent yield of this reaction. Okay, so now you need to go ahead, pause the video, and do this problem by yourself. And so as usual, you're going to find the moles first. The moles of titanium chloride are going to be this times 10 to the third. I'm converting the kilograms to grams. And you divide it by the molar mass of the titanium chloride, which is titanium. So that's it's a light metal. So that's about 47.9. Fine. So, and then you have 4 chlorines. So times 35.5 plus 47.9. So this should be 189.9. Okay, so let's divide by this. So I've got, it's about 15 moles. I've got about 15 moles. Now, the moles of the magnesium is going to be 1.09 times 10 to the third divided by 24. Divide by 24. So this gives me 45.4 moles. Okay, now let's determine which one is actually the limiting reactant. Magnesium here goes 45.4, and so according to that I gotta get the half of that. So divide this by 2, I'll have 22.7 moles of titanium formed if this was the limiting reactant determining the process. But I gotta also check this one. Titanium chloride is 15 and ratio is 1:1, so titanium chloride is going to produce 15 moles. Therefore, because it is producing less, then it is actually the limiting reactant. This right here is the limiting reactant. So 15 moles is the theoretical yield. I only need to convert this to mass. So the mass of the titanium, then the theoretical yield is going to be 15 moles times, so again that was 47.4 47.9, so 15 times 47.9, so I got 718.5, and that's how much we expected to have. That's the theoretical yield, but now it tells us that the actual yield, what was obtained, was 597. So the percent yield is going to be 597 divided by 718.5 times 100%. 597 divided by 718.5. So that's 83